Hi, thanks for joining me today. I've got a cool number theory problem I want to share with you. This comes from the 2002 IMO shortlist. So it was one of the problems which was submitted for the IMO but didn't make it to the final paper. So this is what the problem is. We want to find the smallest natural number n, so the smallest positive integer n, such that the number 2002 to the power of 2002 can be written as the sum of n cubed numbers. Okay, so we want to write 2002 to the power of 2002 as the sum of n cubes, and we want to find the smallest possible n that does that for us. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so to get the solution to this problem, you've just got to kind of try different avenues of thought, and eventually you'll end up at the right one. But there's no sort of real strategy to this problem apart from trying some different routes. So the first thing we're going to do is consider something which might seem a little bit weird, but we're going to just consider cube numbers mod 9. And then we'll see why that's important in just a second. So firstly, any positive integer can be written, or any integer can be written in the form it's either a multiple of 3, it's 1 more than a multiple of 3, or 1 less than a multiple of 3. So it's one of those three options. So any number t, any integer t, we can write in the form 3k plus r, where r is either -1, 0, or 1. So you can think of r as sort of like a remainder term when we divide by 3. So then when we consider t cubed mod 9, in other words, a cube number mod 9, it would always be, well, if we just use a binomial expansion on this guy here, this will be 3k plus r cubed, which is going to equal 27, or let me write it on the next line, 27k cubed plus 3 choose 1 times 9k squared times r plus 3 choose 2 times 3k times r squared plus r cubed. Okay, so that just comes from the binomial expansion, but when we consider this guy here, mod 9, 27 is a multiple of 9, 9 is obviously a multiple of 9, so these two terms here vanish. This one here, when we look at 3 choose 2, that's just 3, so we've got a 3 times 3 here, so this here is a multiple of 9 as well, so that vanishes mod 9, so all we're left with is r cubed. So this guy here is congruent to r cubed mod 9, like so. Okay, so that basically tells us that any cube number is congruent to the sort of remainder term cubed mod 9. But remember, what is r? It's either -1, 0, or 1. So in particular, any cube number, if you look at this guy here cubed, it's either equal to -1, 0, or 1, depending on what r started off to be. But in particular, that tells us that any cube number, when you look at it mod 9, must either be -1, 0, or 1. So let's remember that. Let me clear up the whiteboard and we'll continue. Okay, so we've just shown that for any integer t cubed must be -1, 0, or 1 mod 9. And I've also written down two facts about the number 2002. Firstly, 2002 is equal to 9 times 222 plus 4, and 2002 is also 3 times 667 plus 1. And now these might not seem, or it might not seem clear why these are important, but they're going to become important in just a second. We're going to consider 2002 to the power of 2002 mod 9. Okay, so we want to consider 2002 to the 2002 mod 9. Well, 2002 is just 9 times 222 plus 4, but its remainder term is just 4 when we look at that mod 9. So this thing here is just congruent to 4 to the power of 2002 mod 9. But now 2002, if you write it in this way, we can write it as 3 times 667 plus 1. So this thing here is just the same thing as 4 to the power of 3 times 667 plus 1, mod 9 again. But then we can write this as 4 to the 3, so 4 cubed then raised to the 667 times 4. So this thing here is just 4 times 4 cubed to the 667, like so. Now 4 cubed is just 64, but when we look at that mod 9, 64, remember 63 is a multiple of 9, so that means that 64 is congruent to 1 mod 9. So this thing here is just congruent to 1, and then of course 1 to the 667 is just 1, so all in all, this guy here is just congruent to 4 mod 9. Okay, so we've shown that 2002 to the power of 2002, sort of the main number that we're considering, is congruent to 4 mod 9. But what does that tell us? Well, if we go back to what we proved just a second ago, that any integer cubed must be -1, 0, or 1 mod 9, that tells us that we cannot write the number 2002 to the power of 2002 as the sum of 3 cubes or less. So if we're going to write the number 2002 to the power of 2002 as a sum of cubes, we're going to have to use at least 4 cubes, because if we try using, say, 3 cubes, then we have to look at this guy here. There's no way we can add 3 numbers from that set and end up with 4. Okay, and similarly, we can't add 2 numbers from that set and get 4, and we can't add 1 number from that set and just get 4. Okay, so that tells us that the solution to our problem n must be at least 4. So we need to use at least 4 cubes to, we need at least 4 cubes to sum together to make the number 2002 to the power of 2002. Now, I claim that the answer n is exactly 4. So in other words, we can write 2002 to the power of 2002 as 4 cubes, as a sum of 4 cubes. But let's see why. Let me clear up the whiteboard, and then we'll show that we can write it as a sum of 4 cubes. Okay, so to show that 2002 to the power of 2002 can be written as the sum of 4 cubes, let me just give you an example. But before we do that, let's have a bit of exploration with the number 2002. Can we write the number 2002 as the sum of 4 cubes? Because once we've done that, perhaps that can help us to find 4 cube numbers which sum to 2002 to the power of 2002. Now, if you think about it for just a second, you can hopefully get quite an obvious way of summing 2002 as a sum of 4 cubes. You can just write 2002 is equal to 10 cubed plus 10 cubed plus 1 cubed plus 1 cubed. Okay, because of course 10 cubed is 1,000, so 1,000 plus 1,000 plus 1 is 2002. Great. Now, recall that 2002 is the same thing as 3 times 667 plus 1. So this is one of the facts I had written down earlier. 3 times 667 plus 1. And now, we're summing 2002 as a sum of cubes, and we've got this 3 here, which perhaps if you think of this 2002 as the thing that's going in the exponent of the 2002 to the 2002, maybe we can use this to our advantage. Okay, so let's see if we can write 2002 to the 2002 as the sum of 4 cubes. Well, this thing here is just 2002 to the 3 times 667 plus 1. Okay, but of course we can just write this thing here as 2022 to the 667, that guy there cubed, times 2022, right? But 2022 we can write like this thing here. So this is just 10 cubed plus 10 cubed plus 1 cubed plus 1 cubed. Cool. So we've got 4 cubes here summed together, and then we're multiplying that by this big guy here cubed. Okay, but if we sort of just distribute this into the summation, we're going to get the sum of 4 massive numbers cubed. So I'll just write this down. If I bring this guy into this one, I can write this, the first term, as 10 times 2022, not 2022, 2002, sorry. Yeah, that's the only time I've written it, sorry. 10 times 2002 to the 667 cubed, plus 10 times 2002 to the 667 cubed, plus 2002 to the 667 cubed, and then finally 2002 to the 667 cubed, like so. Okay, so this thing here, when you sum it up, you're going to get 2002 to the power of 2002. Sorry, lots of 2's floating about. I got a bit confused there. I've written 2022 here, whoops. Okay, I hope I haven't written 2022 too many times. Anyway, so all we've done here is just taken this and distributed it into here, and we can clearly see this is the sum of 4 cubes, and it sums to give us 2002 to the power of 2002. I said it right that time. Yeah, so that's a solution, and that shows that the minimum n is 4, because we showed that it has to be at least 4, and we've given an example for when n equals 4, so we're done, and yeah, that solves the problem. I hope you have enjoyed this number theory problem. Yeah, thanks for watching. I'll catch you in the next one. Have a great day.